Welcome, everyone. Thank you for, got a technical glitch. Okay, sorry about that. Technical difficulties because we're doing this in person and we're hybrid. So we're sending this to a YouTube stream and Facebook Live are both picking this up. So hello, online audience. Thank you for joining us. I'm Dr. Cameron Hummels. I'm an astrophysicist here and I'll be your MC for this evening's event. Thank you for joining us. A quick layout of what we have in store for tonight. In a couple of moments, I'll introduce our speaker who will talk for roughly 30 minutes about black holes consuming stars. Super interesting topic by one of the experts here at Caltech. And when she's done, we'll take questions on the content of her presentation for 5, maybe 10 minutes. And then we're going to do a split, and there will be 2 separate kind of concurrent events that are going on, and you're free to go back and forth between the 2. We'll immediately set up this table here, a panel Q&A consisting of Yuhan, the speaker tonight, myself, and 2 other astrophysicists in the department who work on other areas of astronomy and physics. And we'll take audience questions on anything related to astronomy or physics or space science that you may be wondering about. And we'll do that for about, until 9 o'clock, so around 90 minutes or so. And at the same time that we're doing the Q&A panel, there are telescopes set up on the athletic field just behind us. So we'll have 3 telescopes out there. They're setting them up right now. And in terms of targets that are visible tonight, Mars is visible. Jupiter will probably still be visible, at least for the first part of the evening. And then, so that's it for the solar system. And then probably the Andromeda Galaxy, the Orion Nebula, the Pleiades star cluster, and a few other targets as well. So plenty of things to see. Oftentimes, though, if everybody gets up out of their seat and rushes out to the telescopes, then you have lines. So you're intrinsically just waiting. So oftentimes it makes sense to have a few people stick around and ask questions if you're interested, and then go out later, or vice versa. You may have heard about this new comet that's visible in the sky. Sadly, it has not yet risen for the evening. It rises at about 11 p.m. or so in the northeastern part of the sky over there. And it stays up the rest of the night. So I got up at 5 a.m. yesterday and took some pictures with the telescope, which look really cool. I'll try and show them later. But sadly, we won't be able to see that comet, which is kind of a shame because the comet was discovered by a team here at Caltech. The ZTF team was responsible for its discovery last year. And so if you want to know more about that, feel free to ask our Q&A panel after the presentation, or I'm also going to try and put together like a short YouTube clip that shows pictures and explains more about the comet. So stay tuned on our YouTube channel and social media and so on and so forth. But other announcements, this event is part of our stargazing lecture series. They happen once a month on a Friday night. Our next one, I don't remember off the top of my head, sometime in February. And they're always free and they're always open to everyone and live stream. So our last 7 years of these events are all on our YouTube channel. So there's lots of good content there if you want to check it out. And additionally, we have another series of events called Astronomy on Tap. Those take place at a local bar and restaurant in Old Town Pasadena on Monday nights, once a month. And they're a little less formal because they're at a bar restaurant. There are a couple of 20-minute presentations given by scientists here and at the Jet Propulsion Laboratory and UCLA and so on. And we also have space-themed pub trivia, and we have live music, and there's also telescopes at that. So our next one of those is a week from this coming Monday, so January 30th. And the topics that will be discussed are, there's a JPL engineer talking about how rockets work, how rocket physics works. And he has a bunch of really cool footage. He was at the launch of the Artemis 1 mission a couple of months ago, and he has this really cool image, movies of that. And then the other speaker is a graduate student scientist here at Caltech who works to control some of the Mars rovers, Mars 2020, Perseverance. And so she's going to talk, she's a scientist studying Mars surface features, and she's going to talk about Mars and controlling the rover and all of that. So check that out if you're thus interested. But enough about me. Our speaker tonight is a 4th-year PhD student in the department. Fifth year PhD student in the department. She's finishing this spring. She got her start. She's from China, from Beijing. She went to Peking University for her undergraduate. She's been here for 5 years, studying black holes. and the effect they have on their environments. And she's going to be, when she finishes her PhD this spring, she's going to be starting a position at Berkeley in Northern California. So please welcome almost Dr. Yuhan Yao.
Thank you, Cameron, for the introduction. Hello, everyone. Thank you for coming here tonight. As Cameron said, my name is Yuhan. I'm going to talk about fireworks that come from black holes devouring stars. So I want to start by showing this image obtained by the Hubble Space Telescope in the Hubble Deep Field. In this image, almost every celestial object you see is a galaxy, and the galaxies are bright because of the stars within them are emitting light. Some galaxies like this one show a spiral pattern of arms. The arms are areas of high densities where new stars are being formed. The spiral arm rotates around the central region, which contains old stars. Some other galaxies, like this orange one, has a more or less spherical symmetric morphology. That's because the stars within them have random orbits and they distribute more or less evenly within the galaxy's volume. A typical galaxy like our Milky Way has 100 billion stars. And among the many galaxies in the universe, about 5 to 10% of them are called active galactic nuclei. That's because their central region is very bright and active. The amount of light that is emitted from the galaxy center is so bright such that it cannot be explained by the light emitted from stars. And also in a fraction of those active galactic nuclei, we observe this strong bipolar outflow that seems to be ejected from the center of the galaxies. And the amount of energy that is required to power this large-scale outflow is also so extreme, such that it cannot be explained by the star's activity. So astronomers think that in the center of an active galaxy, there exists a supermassive black hole. The black holes do not themselves emit light, but they can exert strong gravity on the surrounding materials, which attract the nearby stars and gas to move closer and fall into the black hole's event horizon. The event horizon of a black hole is a surface within which the escape velocity exceeds the speed of light. So if matter and radiation fall into the event horizon, they will never be able to get out. So eventually, the mass of the nearby gas and the stars are accumulated to the black hole. Astronomers call this process accretion. And because the accreted material always have some initial angular momentum, the accretion process normally forms a disk. So going back to this picture, the majority of galaxies you see are not active galaxies. So if there are also supermassive black holes in their centers, then we call these black holes dormant. Or in other words, they decide to go on a diet. They are not in the mood to emit bright lights by actively accreting the surrounding materials. And the best way to look for such a dormant black hole is to look in our own galaxy. For historical reasons, the center of our own galaxy is called Sag A star. Sagittarius is the name of the constellation. A is just an arbitrary letter, and the asterisk was attached because the initial discovery was considered very interesting. It was first identified as a radio source in 1954. If Sag A star is a truly supermassive black hole, then it should exert gravity onto the nearby stars, and the nearby stars should orbit around it. And by measuring the orbital motions of the nearby stars, one can infer the mass of Sag A star. The physics is very straightforward, but the measurement is very hard to make. Because as the star's light travels thousands of light years to reach the telescopes on Earth, they need to go through the Earth's atmosphere right at the end of their journey. And the cold and hot airs in the Earth's atmosphere are always moving, which causes the starlight to twinkle, showing a somewhat blurred image. So to solve this problem, astronomers came up with a breakthrough technology called the adaptive optics, which uses the laser's light to correct for the atmosphere's distortion. So here is the Milky Way as seen from the Mauna Kea Observatory, and down here are two 10-meter Keck telescopes. The yellow beams are lasers that's sent to your target of interest. Once the laser's light reaches about 90 kilometers high, it will excite a thin layer of sodium atoms, and this will provide a point source that can act as an artificial star for the adaptive optic system. And by modeling the wavefront from the artificial star, astronomers can correct for the distortions from the atmosphere. This will allow us to have much sharper images. And using this technique, Professor Andrea Getz and Professor Reinhard Genzel have independently measured the motion of stars in this very dense galactic center region. And they independently inferred that the mass of Sag A star is about 4 times 10 to the 6th the mass of the sun. In other words, it's so heavy such that it can only be a supermassive black hole. So this is a video created based on the UCLA group's result. Each individual dot represents a star in the vicinity of the Sag A star black hole. We can pay attention to the angular scale of this image. This is few times 10 to the -5 degrees, which is very small. For reference, the moon spans roughly half a degree on sky. So this method of directly measuring the orbit of galactic center stars can only be applied to weigh the nearest supermassive black hole, which is the black hole in our own galaxy. In principle, there is another effect that astronomers can make use of. General relativity predicts that light will be bent around black holes. So this will create a shadow with a photon ring surrounding it. For example, this is a picture in this Hollywood movie Interstellar showing a rapidly spinning black hole as it would be viewed from a nearby observer. And to show this more clearly, here is a recent calculation assuming a spherical accretion flow surrounding the black hole, and each individual line are routes of light rates that's around the black hole to reach a distant observer at the far right side of this picture. The X and Y axis are given in units of gravitational radius, and this paper uses the event horizon radius of 2 gravitational radii to depict the surface of the black hole. The light rays are color-coded by where they peaks in terms of the light intensity. So for example, this particular ray started from here, it gets bent around the black hole, climbs out of the gravitational potential of the black hole to reach the observer at the far right side. Oh, I just realized that you cannot see my cursor, sorry. So due to Doppler beaming effect, part of the light ray that's coming inside the black hole will be significantly brighter than the portions that's coming outside of the black hole. So you can see that this particular light ray, it gets bent, and then its intensity in the incoming part is the highest, and the outcoming radius of the light ray is about 5.2 times the gravitational radius. So for an observer on the right, they will see a shadow surrounded by a photon ring, where the shadow's radius is about 5.2 times gravitational radius. In other words, about 2.5 times the event horizon radius. So although this effect has been known for many years, it was not until recently that the first black hole shadow image was ever obtained. Because again, to resolve the shadow, we need to have very high angular resolution. To do a simple calculation, we can take the values from Sag A star. To resolve the Sag A star shadow, we need to achieve an angular resolution on the order of 10 to the -9 degrees or even less. And this can only be done with an Earth-sized telescope. And this is only possible with the technique called very long baseline interferometry. You might have heard about the Event Horizon Telescope, but it's not a single telescope. It is a global network of radio antennas where each individual telescope receives the signals from the black hole. The signals gets recorded onto the hard disks. And then all the hard disks are shipped to correlation centers, which are supercomputers that combines the different signals together, realign the signals to create this virtual telescope with the size of the Earth. So using the Event Horizon Telescope, people have obtained the shadow image of two supermassive black holes. On the left, you are seeing the supermassive black hole in the center of M87. It is released in 2019, and on the right side is the shadow of Sag-A star released last year. You may notice that the shadow images are not exactly the same as the simulation image that I've shown before, because the real accretion flow are never perfectly spherical symmetric, and our viewing angles are also different. So just to briefly summarize what we have learned so far, we have talked about 3 ways to probe the existence of massive black holes in the center of galaxies. First, around 5 to 10% of galaxies are already active galaxies. Their central supermassive black hole actively accreting surrounding materials, producing copious amount of energy and radiation. And second, by measuring the motions of stars in the galactic center region, one can infer the mass of the central compact object. But this method can only be used to infer the mass of Sag-A star. And last, by obtaining the shadow images using radio very long baseline interferometry, one can also measure the mass of the black hole. But again, this method can only be applied in the nearest supermassive black hole, Sag-A star and M87. So one natural question that arises is, how do we probe the rest of the dormant black holes? How do we even confirm that the rest of the galaxies also have a supermassive black hole in their centers? So here comes tidal disruption events, which are astrophysical phenomena that can awaken a dormant supermassive black hole. But before talking about TDEs, I want to first talk about tidal force. You may know that the ocean's tides is a result of the tidal force from the moon. If we simplify the Earth as a solid sphere with a layer of water, then different parts of the Earth experience a gravitational force from the moon with different magnitude. The magnitude is inversely proportional to the distance to the moon. For example, point A is the closest to the moon, so the attraction it experiences is the strongest, and the displacement under gravity is the largest. Point C is further to the moon, so the attraction is smaller and the displacement is also smaller. Point B is in the middle of the Earth's sphere, so the gravitational force is somewhere in the middle between A and C, and it also gets a displacement. So in short, tidal force results from the difference of gravitational field experienced by an object across its physical extent. The effect of tidal force is to deform the shape of a body without a change in volume. In the case of the Earth, the spin period is 24 hours. So as we rotate along with the Earth, we will see 2 high tides and 2 low tides every day. And the same tidal force also exists between stars and massive black holes. If a star is very close to a massive black hole in the center of a galaxy, then it will be deformed by the tidal force to an ellipsoid. And if the motion of the star happens to be moving in the direction to the black hole, then as it gets closer to the black hole, the tidal force gets stronger and the deformation gets more and more extreme. So what I'm going to show next is a simulation of the whole tidal disruption process. This is not real observation, but should give us an idea of what's happening in the process of a TDE. The blue point is a star, and this is a galaxy with a supermassive black hole in the middle. So as a star gets too close to a supermassive black hole in the center of a galaxy, it will be tidally deformed and spaghettifies into an elongated stream. Roughly half of the stellar stream remains bound to the black hole. They will fall back to get accreted. And this will produce an electromagnetic flare that people can observe. And by observing the tidal disruption events, one can infer the existence of supermassive black holes. The theoretical prediction first came in 1988 from a British astrophysicist, Martin Rees. And then people further postulated that tidal disruption events should be bright in both the optical ultraviolet light as well as the X-ray light. So if we look at the electromagnetic spectrum, the optical light has a wavelength about 500 nanometer. This is the visible wavelength that you are seeing here. This is where our human eyes are most sensitive to and where the lights from the sun is peaking at. But if we go to shorter wavelengths, or in other words, higher energy, we will first have ultraviolet light and then X-ray light. The X-ray is the same X-ray light that doctors and dentists use to study our body, the airport security use to study our luggage. And the Earth's atmosphere is actually opaque to X-rays. And in order to detect X-rays from astrophysical sources, we need to send a telescope to space. In the case of a tidal disruption event, the newly formed accretion disk emits primarily X-ray light. And there will be outgoing materials from shocks and winds. And this part, the green part, mainly emits UV and optical light. So ever since the theoretical prediction in 1990s, people have been trying to find tidal disruption events. And how do we do this? Well, TDEs will appear as a new type, one type of transients, which are astrophysical sources that vary in brightness. So to search for such cosmic fireworks, one can take images of the night sky, and by comparing two images, we can find new sources that appear on the sky. For example, if I say I have a beautiful image of this pinwheel galaxy at a certain time, and after a few days, if we take another image of the same galaxy, and by comparing the two images, you can notice that there is a new source right at the edge of the spiral arm. In this case, this new source is a supernova, which comes from the explosion of a star. But you can imagine that if a new source appears in the center of a galaxy, then it is very probable to be a tidal disruption event. So using this method, the first TDE was identified in the X-ray sky by the Rosette X-ray satellite. Here shows the X-ray light curve. And then afterwards, a few more were discovered by optical sky surveys, such as the Sloan Digital Sky Survey and the Pan-STARRS survey. However, these old sky surveys either focus on a small region of the sky, or they have relatively shallow sensitivity. So in combination, those surveys only find 1 to 2 TDEs per year. Statistically, for each galaxy, we need to wait more than 10,000 years for an unlucky star to run into the very central region of the galaxy to be consumed by a black hole. So in order to find more TDEs, we need to simultaneously monitor thousands to millions of galaxies. And from this perspective, we need an astrophysical survey with first a large field of view such that we can image the entire accessible sky very fast. And second, we need relatively good sensitivity such that we can detect very faint sources. So here at Caltech, I'm part of this Zwicky Transient Facility collaboration, which uses the 1.2 meter telescope at the Palomar Observatory to take images of the entire northern sky every 2 days. And this is named after the Swiss astrophysicist Fritz Zwicky. He spent most of his time at Caltech. And from 1937 to 1948, he supervised the construction of this telescope, which at that time had a very pioneering design. So this shows the internal structure of the 1.2 meter telescope. The light comes from the upper right side it first goes through the lens, and then it's being reflected by the primary mirror, and then it's focused at the focal plane where the camera is put. Before the Zwicky Transient Facility started in 2018, this telescope was already doing a sky survey. But at that time, the field of view was only 15% of the current ZTF field of view. So you can imagine that it's rather challenging to build this much bigger camera to put it in the focal plane without blocking light that's coming from the sky to reach the primary mirror. So this video shows some of the commissioning work being done here, both at the lab downstairs and also at Palomar Observatory, which is a 3-hour drive down to San Diego. There were engineers working in the clean room, and they managed to get all the delicate sensors together into this very tight area. The exposure time of each individual ZTF image is only 30 seconds. And ZTF is also a multi-band survey. It has 3 different filters. Yeah, this shows the camera, which has 16 CCDs together. This is a robot that can automatically change the different filters within 30 seconds. And ZTF is fully robotic, fully automatic. No one needs to stay up late at night to operation. And the telescope sleuths in position under a computer control and settles in position within 8 to 9 seconds with the shutter closing. What you are seeing here is the first light image obtained by ZTF at the end of 2017. This is Orion Nebula, which is a pretty star-forming region in our own galaxy. So ever since ZTF started in 2018, it has been a great discovery engine for all types of transients. And in particular for TDEs, before ZTF started, we only have 1 to 2 per year. And afterwards, ZTF alone can find 10 to 20 per year. So here I'm showing the real data from a TDE discovered by ZTF. The name of the source is AT 2021 EHB. AT stands for astronomical transient. 2021 is the year of discovery, and EHB is just 3 random letters generated by the naming system. So the red data points are optical light curves obtained by ZTF. And the purple data points, it's a ultraviolet light curve obtained by the Swift satellite using the ultraviolet telescope. So you can see that in the case of a TDE, it is brighter in the ultraviolet light, which tells us that the temperature is very hot. So by measuring the temperature, brightness, and duration of this event, we can infer what's the speed that the star is being swallowed, and how does the eating rate evolve as a function of time. But as I mentioned before, the UV and optical light only traces the outflowing materials. But in order to see what's going on in the vicinity of the black hole, to really watch the high energy activities just outside of the event horizon, we need to use X-ray telescopes. So here are some major X-ray telescopes in the world. In the lower energy X-ray light, we have the NASA Chandra, Swift, and NICER telescopes, as well as the European XM Newton telescope. And going to the higher energy X-ray, we have the NASA NuSTAR telescope. It's worth mentioning that the principal investigator of NuSTAR is Dr. Fiona Harrison, who's a Caltech physics professor. And the Science Operations Center of NuSTAR is just upstairs on the 2nd floor. So for my PhD thesis, a major part of my work is to try to find tidal disruption events with ZTF at the very beginning, and then alert the various X-ray observatories to say, hey, there is a new TDE. It probably has very interesting X-ray emission. So could you please point your telescope to the direction of this cosmic firework, such that we can learn what's going on in the vicinity of the black hole. And if they think, yeah, that seems to be something that's worth looking at, then together with the UV and optical data, we will have simultaneous X-ray observations. So here I'm showing the data of the same source as before, but here in the bottom panel is the X-ray light curve. The black data comes from the Swift satellite, and then yellow data comes from the NICER satellite. They are complementary to each other. And the surprise that comes is that you can see the X-ray light does not track the same trend of the UV and optical light. For example, if we focus on between 100 days and 200 days after the optical peak, sorry, the UV and optical data in this time period stays relatively flat. But you can see the X-ray is doing this crazy flux change. And in particular here, it has dropped by an order of magnitude within just 1 day. So what's going on here? In order to figure this out, we did a very careful analysis of the X-ray photon spectral energy distribution. And we think that the most likely cause for the X-ray flux changes is due to the gradual formation and collapse of a region called the corona. The corona is a cloud of ionized plasma where the atoms are stripped of the electrons. The corona emits higher energy X-rays than any other parts of the accreting black hole system. This term was actually borrowed from a solar phenomena. The solar corona refers to the outer part of the sun's atmosphere, which has very high temperature and very low density. The sun's magnetic field affects the particles in the plasma to form these beautiful pictures, such as this you're seeing here. And in previous observations of other accreting black holes, people have seen that under certain conditions, a corona can form above the accretion disk, and they usually appear together with jets that's coming out in the two directions along the black hole. This is an artist's view of the tidal disruption event AT 2021 EHB, where the black region on top of the disk is what we think magnetically dominated corona above the accretion disk. In this case, we know that the corona was formed in about 200 days and then suddenly disappeared within 1 day. But we actually don't know where it comes from or how exactly it gets so hot. So those are our open questions in the TDE studies. And this source is just one example of tidal disruption event. In order to fully characterize the entire population, we need to have a sample of events. So that's exactly where ZTF comes in. Here I'm showing a subset of all the TDEs discovered by ZTF. Each individual color curve belongs to the light curve of one TDE. And you can see that their light curves span a wide range of diversity because no two TDEs are the same. The black holes have different masses and spins, and then stars have different densities and initial velocities. Generally speaking, heavier black holes will produce a TDE with higher peak luminosity and longer durations. So using TDEs, we have inferred that the space density of black holes from 10 to the 5 solar masses to 10 to the 6 solar masses in this range remains relatively flat. And this is very interesting because if we look at the mass distribution of compact objects, previously we don't even know if intermediate mass black holes below 10 to the 6 solar mass exist. But now at least we know that there is no shortage of black holes within this mass range. But if we want to go below that, if we really want to probe TDEs hosted by 10 to the 4 solar mass black holes, then the sensitivity of ZTF is not deep enough. But luckily, 2 years from now, we will have the Vera-Rubin Observatory large survey of space and time. And this is a factor of 50 deeper than the Zwicky transient facility. So future TDE studies with LSST will help us to further understand the black hole demography. So just to summarize, I hope I have convinced you that black holes exist ubiquitously in the center of galaxies. And we have learned that to destroy a star, the black hole can use its tidal force. We have also talked about how to find tidal disruption events using sky surveys. And finally, I have shown some recent results about how we have understand how the black holes manipulate its surrounding materials while the star is being consumed. So with that, thank you for listening. I'm happy to take any questions.
scale? What would we be looking at?
So this the radius of the disk is about a few times a AU. So 1 AU is 7 times, is about 10 to the 13 centimeter. So this is a few times 10 to the 13 centimeter. And the event horizon of the black hole is about an order of magnitude smaller than that. Yeah.
And just for reference, an AU is also the distance separating the Earth and the sun. It's hard to think of it in centimeters and orders of magnitude like that. So yeah, solar system scale.
Yeah, please.
Here, I'll pass you the microphone so our online audience knows what you're asking as well.
Do TDEs emit gravitational radiation?
TDEs do not emit much gravitational radiation because the star is not dense enough. But if the star is a white dwarf, if there's a white dwarf being disrupted by the black hole, then we might expect, I think it's long wavelength gravitational wave, which can be detected by the next generation gravitational wave detector, LISA. It's going to happen in 10 years from now. Yeah. Yeah, please.
Can you just play the animation again? Oh.
Sure. Yeah, this is a star. It's coming closer and closer to a black hole, and it's tidally deformed, and then it spaghettifies into this elongated stream, and some part of the stream comes back. Sometimes this also produce jets.
Are the jets part of
Are the jets part of the star, or are they another emission from the black hole?
The material from the jet should be coming from the star, but it's very low density. And we think from observations, only less than 1% of all the tidal destruction events launch relativistic jets.
So for me, this is the first time that I hear about solar corona. And my question is, how is it related to the sun? Like, can you tell more about it? I guess.
So you know the sun has a photosphere. Its temperature is about 5,000 K. But above that photosphere, there is a large region of corona where the temperature is actually 10 to the 6 K. It's much hotter than the photosphere, but the density is very small. You cannot observe it during a normal time, but when there is a solar eclipse, you can observe maybe the very diffuse emission from the outer parts of the sun, and that's partly coming from the solar corona. Not sure if that's I think the solar corona also partly contributes to solar winds, which are very high-speed particles that can reach the Earth. But because our Earth has also a magnetosphere, it can protect us from being damaged by the solar wind.
And just to add on to what Yuhan said, so we don't fully understand the generation of the solar corona. And so there's a mission in space called the Parker Solar Probe that was launched a few years ago that's orbiting really close to the sun. And one of its tasks is to better understand the conditions that give rise and the mechanism that gives rise to the solar corona. So it's not just that we don't know, it's that no one knows.
Could TDEs potentially create an environment that would be suitable for quark-gluon plasma around the black hole?
For quark?
Yeah, quark-gluon plasma.
Oh, I don't quite know quark. Sorry.
Yeah, that's a hard question. I don't know that either. Do you know, Ilarian? We can say, well, how about we save that for the Q&A panel after? Okay.
No worries.
Maybe one more question and then we'll switch to the Q&A panel where several of us can get up and field questions. Pardon me.
Thank you for the great talk. My question is, what happens to the stars at the very end as they're being pulled apart? Do the tidal forces affect the ongoing fusion inside? Does it affect the temperature, the luminance, anything like that?
Yeah, I think that's a very good question. I personally don't quite know how the nuclear fusion in the star might be affected, because I think because it's being disrupted, the density in the stellar core will not be high enough to support further burning of nuclear fusions, but I'm not quite sure.
That seems reasonable. Okay. Let's have everyone thank our speaker. Great presentation. Okay, so now is the point at which we kind of break, and there will be two concurrent things that you can do and go back and forth between the two. In a few moments, we'll set up this table and we'll have a Q&A panel consisting of Yuhan, myself, Dr. Ilaria Cayazzo, and Dr. Kyle Kramer, who are astronomers in the department, working on a variety of different things, and we'll be able to field questions on like solar corona or quark-gluon plasmas or whatever, what have you. And so that'll go for another hour and 15 minutes until 9 o'clock. And at the same time, I was just out there, we've got the telescopes set up, looking at various different things in the sky, and that'll go on until 9 o'clock as well. And yeah, our next one of these is Friday in February. I forget which day, but it'll be announced on our website and on social media. And then Astronomy on Tap is a week from Monday at the Doghouse in Old Town Pasadena. So thanks for joining us, and we'll get started with the Q&A panel in just a few moments. All right. Go ahead, take a seat, guys. All right, thanks for sticking around, everyone. Take a seat, please. So now we're on to the portion of the evening where it's the Q&A panel. Thanks for sticking around for it instead of just running straight to the telescopes immediately. We have a panel of astrophysicists here. We've already heard from Yuhan, who gave us this wonderful presentation. We also have Dr. Kyle Kramer and Dr. Ilaria Caiazzo and myself to handle questions. So what I'll just do is allow them to give kind of a 2-minute introduction for each of them so you know what sort of science they work on. And then we'll start fielding questions both from you as well as from our online audience. I'll periodically go and check what questions people are asking. So Ilaria, do you want to?
Thank you. Hello, everyone. My name is Ilaria Caiazzo. I am a postdoc here at Caltech. I did my PhD at TBC in Vancouver. I'm from Italy. And I work on compact objects as well, but way less massive than Yuhan's. So I work on white dwarfs and neutron stars.
Hello, I'm Kyle. I am a postdoc here, and I did my PhD at Northwestern in Chicago. So I guess the best way to describe what I work on, so instead of stars smashing into black holes, I work on when black holes smash into black holes. And instead of emitting bursts of light, they emit bursts of gravitational waves, which we have just attained the ability to detect as of 2015, so about 7 years ago. So it's a new field in astronomy that's very exciting.
Trying to run between the online questions as well as be part of the panel. So I'm Dr. Cameron Holmes, and I do computational modeling of how galaxies form and evolve. And in particular, I try and study the outskirts of galaxies. So normally when you think of a galaxy, like they're observing the Andromeda galaxy outside or the Milky Way, you think of the disk part of it, but it turns out there's a lot of material far, far beyond that, but it's very low density and it's almost impossible to see by its light alone. But you can see it in other ways through the absorption of light that's passing through it. And so I try and make models of ways in which we can understand what's going on from this invisible gas. Yeah, that's one of the things I work on. So, okay, so we'll open it up. There are already some questions online, but you guys get first dibs since you came to an event. No offense, online audience. So if people have questions about astronomy or space science, I'm happy to have you guys ask them, and we'll see if we can field them. And try and make sure to ask it into the microphone so the recording and online audience hears it as well. So are there questions? All right.
This question it's Kyle.
Yes.
What are gravitational waves? Like, I understand that things are drawn to each other through gravity, but if you have two black holes that collide, or I guess they sort of like spin around each other and then merge, and they emit gravitational waves, like what does that look like? Are things drawn towards them? Are they pushing them away? How can I like conceive of this?
I have to make this joke, hopefully. So you look like Einstein, and Einstein, in fact, discovered gravitational waves. So I'm surprised that you're asking this question. Okay, so gravitational waves are basically ripples. They're waves in space and time itself. Okay, so instead of producing like electromagnetic oscillations that can be detected by your eye or a telescope or a radio telescope, gravitational waves basically, as they pass through space, they stretch and pull space. And the way that you can measure gravitational waves are produced by very massive objects that are basically accelerating in unique ways. And that basically then produces this ripple in space that can be detected. And the way that we can detect these ripples in space is because they stretch and pull space. Basically, I'll just draw a quick little diagram. It'll maybe be easier. So the way our detector works, it's an interferometer, and it has two arms that are each about
about a mile long or so, a few miles long. And they send lasers down each of these arms, and then they have mirrors on each of these sides. And because as the gravitational wave passes through space, it causes the length of these tunnels, these arms, to actually change. It stretches and pulls because of this disturbance in space. And this means that as you send a laser down and reflects off the mirror and it comes back, and then you do the same thing over here, because the space is being stretched and pulled, by the time these lasers come back, they didn't actually cross the same distance. So they interfere with each other. And then you detect this interference pattern back at your detector. And then that tells you how much the space was stretched and pulled in these two directions. And then you can use that to measure the amplitude of the wave. And that tells you about the masses of the things that collided to produce the gravitational wave. And so far, the ones that we've detected are coming from either mergers of pairs of black holes or mergers of pairs of neutron stars, or maybe one neutron star and one black hole, but those are a lot more rare. So hopefully that helps answer the question.
Hello. You talked about gravitational waves. Are they affected like by the Doppler effect? Since I know light waves are affected by Doppler effect.
That's a great question.
Yeah, that is a very good question. Yes. In fact, I guess everything we observe out, especially in the distant universe, is affected by the Doppler effect because the universe is expanding. So things get, we call it redshifted.
I think any wave should be,
Yeah.
regardless of the.
And the further away something is, the more it's affected by this Doppler effect, just because the universe is expanding. So things are moving at large velocities. And so this does happen for gravitational waves. And in fact, that's one of the ways we can measure the distance to the things we detect, by how much it gets redshifted by this Doppler effect. So that's a really good question.
Yeah.
I'm going to keep asking about collision of two black holes here. What is the sort of time frame we're looking at between when those, two black holes collide, or one of the scenarios you gave, and when you detect it in your sensors? Like what's that time frame?
Well, it depends on the distance, because gravitational waves, like always, take time to travel towards us. They go at the speed of light. And so if it's, I don't know, what's the closest one?
Binary neutron star was something like that, many millions of light years. So
Yeah, millions. The shortest time scale between one of these mergers and when we have detected was millions of years. Yeah.
Well,
like
light years and thus years. Yeah. So yeah, if something happened closer, like it's kind of like if I clap my hands together and I'm right next to you, you'll hear that almost instantaneously. But if I'm across a few football fields and I clap really loudly, of course, because it has to propagate to you, it's going to take longer. And it's the same thing for this. So we've only detected these events happening at, close astronomically, but still like 14 megaparsecs is like 50 million light years away. That isn't to say that there won't be events that take place closer, and thus it'll be a shorter travel time, but we just haven't yet detected them. Other questions? Can I? Telephone. Yeah, sure.
By how much does space actually stretch and expand space-time?
So the LIGO detectors measured. So LIGO is the primary way that we've been detecting gravitational waves, and the path length, the change in path length that they've measured for these merging binary stars is less than the size of a proton, like a nucleon in a hydrogen atom. So it's like.
I just was
Oh yeah, LIGO. In terms of that size scale, what's the size of a nucleus of an atom? It's like 10 to the negative. I don't know. I'm going to make up a number, and somebody online is
ridiculously small fraction of even like a centimeter. That's like really.
It's a very, very compact center to an atom, and atoms are already incredibly small. So I don't know.
I think I've heard like if if you compare the size of the arms to the distance between the Earth and the Moon, the stretching would be the hair, like the comparison.
So hair on the Earth Moon system.
The hair on the Earth Moon system, yeah.
Other questions, or should I move to the online audience? Oh, okay. I'll let you ask.
How does the mass of like stars when entering a black hole, how does it affect like the luminosity or like the amount of X-ray light that you get?
Yeah, the luminosity typically at first rise for a month to reach 10 to the 43 ergs per second. I'm not sure how luminous that is.
Like what? 1,000,000 times brighter than the sun about?
Yeah, 1,000,000 times the sun's brightness, and then it decays slowly for a couple of months. It depends on the rate at which the star's mass is being fought back to the black hole. Yeah.
So I have a couple of black hole questions from online. Stephen Schreier asked several minutes ago, would you care to hypothesize what the interior of a black hole might look like? Might the interior be bright or without light? Thank you for an excellent presentation.
Thank you.
So what's the inside? Once you go inside that event horizon, obviously this is speculation. We can't go inside of well, we could, but we wouldn't be able to come back out, and we wouldn't even be able to like send information out. That's the whole purpose of a black hole, or not purpose, but that's the whole outcome of a black hole, is that its gravitational pull is such that nothing can escape, not light, not information. So if one were to do a Matthew McConaughey like travel into the interior of a black hole, as he does in Interstellar, would you see a bunch of bookshelves, or would it be a very bright space? Would it be a very dark space? It seems to me it could be very light. The photons are also traveling in. The matter is also traveling in alongside you as you fall in. That light's trajectory is going to be heading towards the central point, towards the singularity in the center, but it could very well be a light space if you're in the path of the photons on their way to you, but you're also getting warped by relativistic effects. So it wouldn't be the first thing on your mind. Getting stretched out would be the first thing on your mind. Yeah, I don't know. Do you guys have anything? We need a GR person here. Guess you do some GR.
I mean, yes, I think it could be. I mean, first of all, when you pass the event horizon, which is, the event horizon is this limit around the black hole where light can, it's so close to the black hole that gravity is so strong that not even light can escape and nothing can escape. Once you pass it, that's it. And I think you wouldn't feel it.
No,
there's no actual limit, you know.
You wouldn't know when you pass that. You'd be like, oh, no.
It's nothing.
Well, for a really massive black hole, you wouldn't feel it, but for a low mass black hole, you would feel it.
You'd feel it because you'd be
tidally destroyed before you got to it. That's true. That's true. You wouldn't
not
feel
a
anything
discrete
different
transition. Yeah.
That's
It would
right.
be nice.
That's right.
Light or dark, I don't know if that even makes sense, because the photons cannot come to your eyes because you're all going in the same, So I don't think it would be light.
I would probably not put my money on it being light.
It cannot go out, but it comes to your eyes.
Okay. Other questions in the in-person audience, or should I go back to online? Okay, here's an in-person question.
I had more of a general question, not pertaining to black holes. What qualities and skill sets do you all think are some of the most important to become an astrophysicist?
Great question. Go ahead, guys. I'll just talk forever if I have the chance. So let everybody else. What do you think, Yuhan? What's a good skill set?
Skill set. They should enjoy doing research. Having fun. I think having fun is very important because it can be a very feedback is very long time scale. You need to wait for a long time for a paper to be published. So yeah.
You need to enjoy doing the work. Sorry.
Well, like in a practical skill, just the ability to computer program. I'd say that's the single most practical skill, even more than math or science background. I'd say, especially when you get to the point where you're doing independent research, being able to computer program is, I don't know, 2/3 of the job description probably. And being able to be creative and come up with ideas is also important. But once you have come up with an idea, you need some of those technical skills. So.
Yeah, I mean, being one thing that it's very different. For example, when you go from school or studying to doing research is, setting in front of something that doesn't have a solution, that is not a right way. And so it can be scary. And so be excited by this, it could be different, we approach it in very different ways. There's theories, there's people that do observations, and but there's always like a big question or many big questions out there that do not have a solution. You have to sit down and figure it out how to get there, and there's no pathway. And so a skill that you have to develop, but it won't come immediately, but it's something that you slowly developing also, especially with interactions with your peers, etc., is this ability of saying, okay, there's no obvious path, there's no obvious solution, but I will sit down and slowly figure it out. And it's something that, it's a big difference from, a lot of other jobs. And it's something that you develop while doing it.
I'd agree with that too. Self-reliance and just confidence in your ability to kind of piece together what's going on. I would also say communicating your ideas to other people. So, Kyle mentioned that a lot of it is writing code, and that is true for coming up with solutions on various different tasks for analyzing your data and interpreting that data. But then communicating the results of your ideas and analyses to other people, either verbally in terms of presentations that you give to the community, or even at an event like tonight, but also being able to write that up in a cohesive way, in a paper that other people will be able to take your main points from it. If you can't do that, then you're not going to go very far. So actually, when people have tried to make predictors, broad predictors of the success of astronomers in the field when they're a graduate student, depending on they can only allow so many graduate students into a program or so many postdocs into a program. And they only have so much information about those applicants. One of the best predictors of success in the field turns out to be how well you can write, which seems kind of counterintuitive, right? We're not in an English department, we're in a science department. And yet people who can write well tend to do better. Anyway, additional questions? I can also go back to the online questions. Oh yeah, is the plasma, the gluon quark plasma? Yeah, here, I'll let you rehash that.
So when I went to the telescope, someone kind of explained to me in why it probably wouldn't exist in a TDE, but more closer to the black hole. But yeah, just what do you guys think about the presence of potentially quark-gluon plasma existing near the environment of a black hole?
let's first define what that is for the audience. So quarks are the building blocks of like protons and neutrons and subatomic particles. So you think of an atom as being, like a hydrogen atom consists of proton and an electron, and sometimes a neutron, depending on the isotope. But then if you break down those protons and neutrons, then you get to these quarks. And thus far, correct me if I'm wrong, thus far, I think we've only been able to find indications of quarks in particle colliders, like the Large Hadron Collider or whatnot. Can't you find quarks in those? Maybe we can't. Maybe they're only a theoretical. Okay, now I'm revealing my ignorance of particle physics. But quarks, there's a bunch of different kinds of quarks. There's top quarks and bottom quarks and up quarks and down quarks and what's the other one? Strange and charm. Ooh, charm, that charm quark. And you put them together in different configurations and you get different particles. And so I guess it's, and gluons are another kind of exotic particle that's for the strong charge. So you have more to say about this than I do. So I'll let you talk because you were the one who wanted to field this. I just wanted to give people context.
Yeah. So yeah, we have seen quarks in colliders, and gluons are kind of like the messengers between quarks. So and they're called gluon because that's what keep the quarks together in a nucleus. But the thing is, the quarks are so extremely tightly bound in the nuclei that to liberate them, you need either extremely high energy, like in a collider, or extremely high density, right? So if you squish protons and neutrons extremely hard, either if they're going very fast, the very high energy part, or if you're squishing them together under enormous pressure, then you can liberate the quarks. And so on Earth, you have liberated the quarks in the colliders, but in space, there are a few quite extreme environments in which you could have a quark-gluon plasma. So it has not been proved, but for example, neutron stars are these stars, they're these dead stars that are, they're as massive as the sun, even a little bit more, but they're incredibly dense. They're about the size of a city. They're like 20 kilometers in diameter. So they're so incredibly dense, especially in the core, that has been theorized that in the core you might have, quarks that are free. They're not bound in neutrons and protons. It has not been proved yet. So I don't think in TDEs you can reach neither those energies nor those densities. So I don't think there is free quarks, but neutron stars could be hosting in the very center free quarks and gluons.
Even at the very center of the accretion disk, would it be dense enough there maybe?
The accretion disks are not very dense.
Yeah, that's true.
Feel free to take off if you got to run or you want to check out the telescopes too. We don't need to hold you here and make it awkward for you to leave. We won't be offended, I promise. Are there additional questions from the audience? Again, we've got online stuff if people don't have questions here. Okay. Let's see. Dusty Wallpaper asks, will we ever find a way to observe dark matter outside of how it affects visible objects, like direct detection of dark matter? What do you guys think? Of how it affects like indirect evidence of dark matter, like in the way that we see galaxies have a flat rotation curve indicates that there's some unseen mass component that we can't directly view. So is there ever a hope? Thanks for coming, guys. Is there ever a hope of directly detecting a dark matter particle? And there are people who are trying to do this. There are labs where people hope that dark matter has some sort of cross section for interaction with visible matter, much that it would produce light. Either here on the Earth, there are labs for doing this, and people also look for in the densest regions where the dark matter density is the highest, in the cores of dwarf galaxies, you have very high everything density, but presumably very high dark matter density. And so the hope is that maybe when things get dense enough, then those dark matter particles might interact with each other, not just gravitationally, but they might actually slam into each other, and that might cause an annihilation event or a collision event and release some sort of light that might be visible, like in gamma rays or X-rays. So people are trying to look for signals of that by taking images of the cores of dwarf galaxies to look for this sort of indication. There's a lot of theorists who are making predictions for different qualities associated with dark matter and ways in which it could propagate to look for this, rather than it like self-interacting dark matter, where dark matter could run into each other and cause this sort of signal. But yeah, so there's a hope. But yeah, please.
So I actually have a program. No, so first of all, we do not know what dark matter is. So there's lots of different possibilities, lots of different theories. It could be a very, very light particle. It could be a heavier particle. We still don't know. We know it exists. You know, it interacts very weakly with anything. So it's very hard to detect it. So I have this program to actually detect directly a type of dark matter, which is called axion. So axion is a predicted particle. It hasn't been detected yet, but it's a possible candidate for dark matter. And so in my program, I studied white dwarfs, and I found this very special white dwarf, which is like very, very tiny, very, very magnetic, very, very hot. And so in the core of this white dwarf, the density might be high enough for this particle to be produced. And so as it gets out of the white dwarf, if this particle interacts with the magnetic field, it might convert into an X-ray. And so I have this program with NuSTAR to look at the white dwarf to see if we can detect the X-ray, which would be at a very specific energy, 14.4 keV. So if we find a line at 14.4 keV, it would be a pretty significant and very direct detection of this particle. Since, my bet would be that we won't see it because if it would be, quite amazing. But so my program is, if you don't see it, we can constrain, the mass of this particle. So we say, okay, it doesn't exist in this parameter space. If we see it, it would be very, very amazing. But that would be a very direct measurement of this particle.
Good. Okay. Any questions here? Okay, a question. I've still got like 6 on YouTube, so no worries, no pressure.
All right, so this question is kind of a little out of scope, but it's for the 4 of you. There's a lot of science. Well, this is about astronomy in Hollywood, right? And so Cameron mentioned the Interstellar. And I think the subject matter expert on Interstellar was from Caltech, Dr. Kip, maybe? Okay, so my question for the 4 of you, have any directors or anybody from Hollywood reached out to you guys to be subject matter experts on movies or documentaries?
This is a great question because, well, first, yeah, Kip Thorne is a professor here, professor emeritus now, right? So he's like a retired professor, but he won the Nobel Prize in 2017 in physics for the stuff with the LIGO gravitational wave detector. And he also wrote the script to Interstellar. So he wrote a book called The Science of Interstellar. I'd say almost everything in Interstellar could be physically possible. Like the time dilation that they get where time slows down when they go close to the planet. Again, spoilers. But in terms of media and in terms of reaching out to astronomers and physicists here, Ilaria has a film that won a number of awards. Tell us about it.
But it's not very scientific.
Scientific. It's science fiction, but it's kind of scientific.
It's a science fiction short movie. It's a dystopic science fiction short movie. It's called The Recycling Man. You can look it online. It's on YouTube, but it has really nothing to do with physics or science.
Yeah.
I produced it. My husband is the director. But you've been contacted many times.
Yeah.
right?
So there's something called the Science and Entertainment Exchange, which is organized by the National Academy of Sciences, which basically scientists, and I encourage you guys to do this, scientists can list their name as being an expert on a particular topic. And then when people from the entertainment creativity side of things, like people who are writing books or writing scripts or directing films, need a subject matter expert on a particular vein of science, whether it's astronomy, whether it's physics, whether it's chemistry or whatever, they can go to this exchange and look up and be like, I need somebody who's a specialist on DNA. And then they'll put them in contact with that person, and then they can ask questions or whatever. So I listed my name for being an expert on galaxies and cosmology and that sort of thing. Like I even put the moon because I did a project on the moon, and that's actually been really helpful. Like 10 years ago when I finished my PhD. And I've been contacted a number of times by directors or writers, and they'll ask me some questions for an hour. And usually it doesn't really ever go anywhere. Like I'll answer questions, I'll do some calculations and give them stuff. And then I never really hear anything further. But 2 years ago, I guess, a year and a half ago, I got contacted by a director who was making a film, and that movie is coming out on Disney Plus in, I just heard from him yesterday. I think in May they set the release date. So on Disney Plus, there's going to be a movie. I think I can talk about it online. Hopefully not going to get in trouble. There's a movie coming out. It's called Crater. It's going to be on Disney Plus. It was already filmed. The description I have for it is it's a lot like The Goonies or Stand By Me, those kind of classic buddy films where there's a bunch of kids and one of those kids is going to leave. And so they have this last adventure, but it's set on the surface of the moon in 200 years in the future. I think it's really good. So they asked me all kinds of questions about science. And so I'm the science technical advisor. So I help them kind of design things and make sure that the science was like kosher throughout much of it. And I haven't seen the final result. So hopefully it's all up to spec, and I don't like have to turn in my PhD for having sent the public astray in terms of the accurate portrayal of science. But the script was really good, and what I've seen of the film looked really good. So keep an eye out for that if you have access to Disney Plus. But that's one way. I mean, it's just kind of random if you get put in touch with the right people that something actually comes out of it. But we are here in Los Angeles, so there's a better chance.
You
than
can
other
hear a lot of
locations.
stories. I mean, Tom Prince was contacted by James Cameron, for example.
Oh, really?
Yes.
Oh, wow.
For Abyss, I think.
Oh, really? For The Abyss?
Yes.
Oh, that's a good movie.
Yes.
Did Tom Prince help with that?
Yeah.
Really? Oh man, his office is right next to mine. He's a professor in the department. I'm going to have to ask him about that. That's cool. Have you guys seen this film? It's from like the mid 1980s or early 90s. It's called The Abyss. It's a Michael Crichton book. And I think it's a Michael Crichton book. Maybe it's not. No, I'm just speaking lies. But it's about a journey into very, very deep ocean and what could be found there. And there's some surprises. I think it's a really well done film. I'm going to have to go compliment Tom Prince. That's great. Good job, Tom Prince. Do you guys want to add to this? You'll be a movie star soon, Kyle and Yuhan. Well, I'm not in those films. I just talk about them. Okay. Let's see. So there's a question here by Girish Ananda. Can time be repulsively additive in the neighborhood of two black holes? Can there be kind of a cumulative effect of time? So I think what he's referring to is time dilation. Is many of you maybe have heard of this. It's where time passes slower or faster in certain situations than it does, time is not just like an absolute. If you're close to a massive object, like we are here on the Earth, time is passing a little bit slower than it would be if we were floating up above on the like further out in space. Or if you're traveling closer to the speed of light, time passes slower. And it's not just your perception, it's actually that time is passing at a different rate. So
your feet are younger than your head.
Your feet are younger than your head. Yeah, that's right. Because your feet are closer to the mass of the Earth. I mean, it's like picoseconds. It's like tiny, tiny, tiny amount, but it is measurable. And so these relativistic effects that are responsible for this can be pronounced. Like in Interstellar, there's at one point, some of the characters go close to us on a planet close to a supermassive black hole. And so time passes, it's like a half an hour down on the surface of the planet, but it was like 9 years for the people who weren't close to it. So you can get these kinds of effects called time dilation. But the question is, could you have cumulative effects from two black holes or two massive objects? And it seems like it distorts the gravitational field, the space-time field. So yes, I would say. Right? I'm the one who talks way too
Yeah,
much.
it definitely is additive, I think, just because if you have 2 10 solar mass black holes, then that's 20 solar masses, and yeah, it should dilate time more. Now, there's probably weird effects if you're like in the middle of like the orbit. That might make things really weird. But if you're, out at some distance where the 2 black holes are kind of act like one bigger one, then it should be additive, the effect.
Or roughly.
Yeah, roughly.
Oh.
So the comet, the recent one, the big one. I know you said it was located in the northeast. Is there like a particular constellation that we could like reference for it? And also, what do you think for students anywhere from K through 12 and lower div college? What would be the best key points to mention about the comet to kids and such?
So the comet, well, I keep talking way too much. You know about the comet. You guys know about, you want to talk about the comet? It's from ZTF. ZTF, good old ZTF. I can talk, you guys talk. I'm going to try and bring up the image that I took yesterday and maybe display it somehow.
I think first thing, it's green. So, which is quite rare for comets. And that's because of some molecules, I don't know which one, that are glowing green. I have to look up. Would you remember what are the molecules that are making it green?
No.
Okay. The other thing is that we just happen to catch these as it's passing by, but it's a very rare event. It has a very long period. It comes from very, very, very far away. To a place that is full of comets.
Watch your head, Kyle. Actually, both of you, perhaps. Well, maybe we'll scoot. Sorry, guys. We'll turn this into a dangerous situation.
It's coming from this place that is far, far away. It's called the Oort cloud, and it's full of comets and icy bodies. But this is a particular long period one. So it comes from very, very far away. And, the period that we measured is about 50,000 years. So we are kind of lucky to see it right now because the next time it's going to come around in 50,000 years. It might not come back just because, when it's out there, it can interact with all of these bodies and so change its trajectory. So it might actually come maybe a little bit sooner or not come at all or come at a different angle. So yeah, I think that's its peculiarity. It's this one of these very, very long periods. So it takes a very long time for it to go around. I don't know. And yes, it was discovered, a few hours from here with the same telescope that Yuhan used to discover the supermassive black holes, because it's the same idea. You look at the sky all the time. This telescope takes pictures and pictures and pictures, and so you immediately notice when there's something new in the sky. Of course, this was discovered last year by ZTF. The comet is only going to be visible by the naked eye in a very dark place now, because it's come much, much closer. ZTF discovered it when it was still very far and very dim.
So here's an image that I took with with my telescope that's being used outside right now. This was at 5 a.m. yesterday, and you can see, first of all, if it were much darker in here. Actually, I'm gonna turn off all the lights. Don't freak out, everybody. It'll be easier to see this though. So you can see the tail structure behind it. The bright spot is obviously that's the core of it. That's the nuclei, the nucleus of the comet. So that's this dirty snowball structure, and then the glowing area around it. That's the coma, which is essentially as it's getting into the inner solar system, sunlight and solar radiation is causing that snow and ice to melt and evaporate and sublimate into this gaseous cloud that surrounds it. And the gas scatters light from the sun, and then it trails behind it. You can see a little bit of the tail, but not a ton. And then obviously all the other dots in the image are stars that are present. So this right now, because it's, I didn't catch everything you said because I was too busy fiddling with stuff, but as it's traveling through the solar system, it's moving across the background of stars that are there. So right now it's, I don't remember in what constellation it sits. I could look it up. I could look it up right now with my phone. But it will continue to move as it travels through the solar system. So right now it rises at about 11 p.m., 11:30 p.m. and is up through the night. But I believe in the next couple of weeks, it'll be rising earlier and earlier. And so you should be able to not have to be a crazy night owl to be able to see it. Physically, I don't know for this one. Generally, the nuclei, the core, the ice block in the center is like kilometers in size, miles in size. So for instance, Halley's Comet is about 6 miles in diameter. This one is probably comparable to that. They tend to be. It's smaller. Okay.
Don't know. Don't remember, but I don't think it's a very big one.
Yeah, a couple miles in size. But then that cloud that surrounds it will be more on par with like the size of the Earth or the size of the United States or the size of California. Even though it starts from this very, very tiny thing, that cloud will change depending on how closely it gets to the sun and how much. It's like you're holding a blow dryer on a snowball from different distances. And as it gets closer, that heat becomes more intense. And so it puffs up the cloud more. So it changes over time, but it's on par with being the size of somewhere from, several hundred miles in size to like thousands or tens of thousands. And then the tail behind it is can be, like an astronomical unit, like the distance from the Earth to the sun in length, just because it's trailing out behind it. Yeah. Oh, here.
So I was wondering, are black holes only destructive, or is there anything that is created within the black holes? I don't know too much about them.
Go ahead, guys. Are things created inside of black holes?
I don't think they can create things inside the black hole, but because they have such strong gravity, they can form the accretion disk surrounding them, and they can also somehow launch jets from the disk. If the black hole is highly spinning, then it's more likely to launch jets. And they can also grow in mass by creating the surrounding materials. I don't know if anything can be created inside. It's
hard to know.
Yeah, well, it's hard to know, but they do grow. So I don't know if you call growing creating. Not really, I guess, but Oh yeah, no, I see. I don't think it can be ruled out that something could be created inside a black hole in an analogous way to how, you know, stars fuse together heavier elements, but we have no idea. It would be some very exotic matter if that does happen. So
That's true.
Yeah, so black holes emit this radiation. It's called Hawking radiation, which is kind of which is was postulated by Stephen Hawking. So if you leave a black hole by itself for a long enough time, it will disappear because it will slowly lose its mass through this evaporation, which is like extremely slow. This particle is extremely like these radiations. You know, we're talking about many times the age of the universe for the big black holes, but they do emit a sort of radiation. I don't know if that's creating something. It's more like losing their mass into the universe. I mean, if you create an extremely small black hole, then it would evaporate very quickly. These are the black holes that Yuhan studies. It would take, you know, like almost infinite amount of time, but not infinite. Finite, but very long.
There's a question here that's specifically on the topic that Yuhan was giving her presentation, and that is, do tidal disruption events, these stars that are getting ripped apart by a black hole, do they result in the creation of elements? In the same way that stars, you get nucleogenesis, where stars cram together and they fuse heavier and heavier elements. Do you also have that in tidal disruption events? And would that provide a way of kind of having some sort of observational signature by looking at the, you know, oh, we see a lot more europium or some weird element that's present here that might be as a function of these stars as they get torn apart?
I think we do see mostly hydrogen and helium in the spectrum, but that's mostly coming from whatever the star already has.
Sure.
And I don't think much newer is being produced.
It's being produced. I guess it's a really short period of time. But on the other hand, like in a supernova, right? In a supernova, there, like a core collapse supernova, there's can be all kinds of production of new elements, but I guess you don't see that in a
no, in supernova, there's radioactive decay from nickel, cobalt to iron, but in a TDE, we don't expect the radioactive decay to happen.
Okay.
Mm-hmm.
But I think if like a white dwarf got tidally disrupted, then you could potentially get new elements because then the
it's
disk
already
would
so
be
dense.
denser, I think I've seen people talk about that.
Really?
I think so.
I don't know.
Yeah, because like in a double neutron star tidal disruption event, then you definitely can get a lot of very heavy elements just because it's so dense.
Even if it's, well, because I feel like the neutron, okay, so the neutron star merger, sorry, we're just going to riff here for a second. The neutron star merger that occurred that did lead to the production of heavier elements, that was from two neutron stars merging. But would you get that same effect from a neutron star that just got close to a black hole? I don't know, because I feel like it gets torn apart as opposed to eventually merging into a denser structure. Yeah.
Yeah, but if I don't think if a neutron star was tidally disrupted by a supermassive black hole, I don't think it would be visible because the tidal disruption occurs inside the event horizon.
Oh.
But I think for a low mass black hole, you would be able to observe the tidal disruption of a neutron star, and I think then because it would produce a gamma ray burst, and people talk about that all the time. So I think it would definitely be able to produce heavy elements.
I guess I'm just thinking of like the beautiful visualization that Yuhan showed, and it had, the star approaching and it gets close and then it's like, wow, and it flings apart into this structure. You think it would occur in that context?
In the center of the star and potentially see carbon and nitrogen.
Right. See that.
Mm-hmm.
But even if you didn't see it, do you think that there'd be an artifact, that there'd be the creation of additional heavier elements than just would already be like in the CNO cycle or something? I don't know. I'm not trying to hold your feet to the fire. I'm just trying to think this out. That's all. Good question, online audience member, Chris Georgie. What's the answer, guys?
Yeah,
I hear
so there's different
process.
types of, the denser the environment, the basically hotter the temperatures you can get in the heavier elements you could eventually create. So there's different types of elements that are known to form in different environments. So I think definitely the disk would get hot enough to be able to produce S process elements. Like those are sort of more similar for like supernova. If you had like definitely, I think for a white dwarf or a neutron star disruption.
Okay.
Even for a main sequence star, I think you would definitely form something. You get some fusion, I think, in the disk, but it might be hard to detect. I don't know.
Okay. Nice job. Nice job. You pass. You pass.
I have two questions, but I think the first one's going to be quick. Which was, you were talking about the shadow of a black hole and how like what I heard was it makes it look larger than it is. When we see the black disk with a little thing around the edge, the actual black hole is not that large. It's smaller. We just, because the shadow, it looks, okay, cool. My second question is, in these graphics that show, let's say the center of something and there's this black hole and then there's plumes of color shooting out of it. It looks like a static picture, taken in time and these things are there. But what's actually happening is those colorful things are moving away. They've been emitted from what's in the center. And this is true of, I guess, any kind of stellar image. Like it's not a static thing. These things are in motion. They've been set off by some explosion or chain of events, and they're moving away or creating a thing. And we just see a snapshot of it. Is that true?
Yeah, the first question, the shadow size is, in the case of a non-spinning black hole, 2.5 times the event horizon radius. And if the black hole is spinning, then it's also, I think, roughly a few times the event horizon radius. The second question, I think you're asking the case of a tidal disruption event. The scale is always moving, the matter is moving, but we can't resolve the scale in very distant galaxies. What we see is always a point source that's limited by our resolution of the telescope. If there's jets being launched, then we can also use the radio very long interferometry to see how the jet evolves. And people do observe that in the case of accreting black holes, as time goes on, if you can monitor the black hole for many years, you do see the jet core slowly extends to longer distances from the center of the galaxy. Yeah.
Okay. Let's see. A question about the massive particles and the dark matter candidates from before. So the question is, aside from the axion, can weakly interacting massive particles be a candidate for dark matter as well? And if so, which is more likely to be dark matter? I guess this harks back to when we were discussing dark matter. Do you guys have anything to say on axions or weakly interacting massive particles? It's okay if you don't. That's not my specialty, certainly. Okay.
WIMPs. That's what it's referring to. I think most of the WIMPs have been ruled out because there's a lot of experiment that has been looking for dark matter and different proposed particles, and WIMPs were this particular type. And so you cannot rule out a particle, you can only rule out a particle to say, okay, I have this experiment, and because experiment is sensitive for that particular particle, if it has that particular mass or that particular state, etc. And so you need several experiments to say, even if you don't, if you find it, you find it. But if you don't find it, to rule it out, you need several experiments. And I think for the WIMPs, they have been mostly ruled out. But again, I'm not an expert.
Yeah, that's a good point. We have a scientist who I've been trying to get for our lecture series, who just joined the department a couple of years ago, who works on dark matter candidates, Catherine Zurich. But thus far, I haven't been able to rope her into a talk. But if I'm successful, that is definitely an appropriate person to ask all of these questions about dark matter's possible nature. Additional questions? I noticed the audience has been slowly tracking back over time. Do you guys have any more questions? We're going to finish up here in the next couple of minutes. Oh, so's my laptop. Got to plug in. Planet 9. Okay. Let me have you say this into the microphone.
So yeah, I'm curious to know what you guys think about Planet 9, whether we ever will find it. And second question is more about the universe. Like, what was the first thing that existed? Was it gravity or something else? And if it was gravity, then how is gravity created out of nothing? And how is time, or the perception of time that we have created, how is that related to the existence of gravity? That's too many questions. But yeah.
Really hitting us with some hard hitters here. First, we'll take them in turn. We'll do the best thing that we can. So, do you guys want to talk about Planet 9? I have to plug in my laptop. It's at 2%, or this live stream is going to end prematurely.
There's people here at Caltech still, like they're looking actively for Planet 9. Yes.
What was?
Yeah. Yes, but again, not a planet person, but Planet 9 is this planet that alleged planet that might be like in the outskirts of the solar system. I don't know exactly what distance is that. Few hundred.
Definitely further out than the other ones.
Further out, all the planets we know, quite a lot further out. And it was theorized because of the motions of some other planetesimals that move quite weirdly, and so it looks like they've been influenced by something far away, something massive far away.
So, like, for instance, this comet, which is on this weird trajectory, there's other things, other planetesimals out of the distant solar system that have weird orbits that have been speculated to be caused by some massive planet that just has yet to be detected, is the idea.
Yeah, so these planetesimals are small bodies. So two scientists here are primarily working on it, a professor named Mike Brown and a professor named Konstantin Batygin. Mike Brown is kind of famously known as the guy who killed Pluto. His Twitter handle is Pluto Killer, because he discovered a lot of these small objects in the outer solar system that were kind of on the size scale of Pluto. And so if you consider Pluto to be a planet, then you also kind of have to consider those to be a planet. So ultimately people were like, well, there's lots of Pluto-like things out there, so let's not call Pluto a planet anymore. So anyway, he's earned the ire of a lot of people because of this demotion. But so they've proposed that this object in the outer solar system, super, super far away, exists. And as Ilaria and Kyle were saying, the way that it's caused the orbits of these other objects to change, or at least that's what their indication is that it's kind of offset. So they noticed that a bunch of these things are kind of on this side of the sun, way out in the outer solar system. And it's suggestive that maybe something else is here and has kind of launched those to be in some sort of resonance against it. But there are counter theories that could be also responsible for not Planet 9 causing this distribution of smaller objects out there. So it's, yeah, it may not exist. I mean, don't tell Mike and Constantine, but it may not exist. And they've been searching for it for a decade or so. Yeah. It's a hard thing to do. Yeah. Yeah, that you're absolutely right. It's like going into a cave with a small flashlight, and just because you don't find that nickel in the first hour doesn't mean there's not a nickel in there. It means that it just might not be something that was easily found. That's a horrible analogy, by the way, but so do we believe that Planet 9? I mean, I don't know, maybe, hopefully. I mean, it'd be pretty cool, discover another object, but it's meant to be massive. Like Pluto was demoted because it was small and it was icy and it was very different from the other 8 planets in our solar system. Whereas this is meant to be like a true planet and like an ice giant, kind of like Neptune or Uranus, which is quite large, much larger than the Earth.
And there's sort of, was Neptune discovered? Was that the one that Herschel found based on like?
No, it's Uranus.
Uranus, yeah. So there's sort of history because Uranus was originally found through a similar method where there was problems with our understanding of the orbits of other things in the solar system. And then it was speculated that there was some new planet. And then basically they looked and found this planet where they thought it would be. And then they discovered a planet through this way. So,
yeah.
So that's, yeah, it's not like the first time people have tried to find a planet through, this way. So
that's how Uranus was detected, and that's how Neptune was detected by Leverrier, as they made these predictions based on slight weirdnesses in the orbits of Jupiter or Saturn. And they were like, oh, the presence of that weirdness could be because there's another object here. Let's look over there. And then they're like, oh, there's something there. We win. But that's also been problematic. So that's how they thought they saw weirdness in the orbits of Uranus and Neptune. And that's why Clyde Tombaugh was looking for what eventually became Pluto, but Pluto was not responsible for the weirdness in those orbits. So it was just kind of lucky that they discovered Pluto. Similarly, they thought they saw weirdness in the orbit of Mercury. And so there was the search for a planet in the interior of Mercury's orbit close to the sun. But ultimately, the weirdness in Mercury's orbit was because of relativity being a truer explanation for why orbits are than Newtonian gravitation. So it's not without caveat, but yeah. Anyway, so we talked about Planet 9. What were the other questions she had?
Was
gravity?
Gravity, yeah. Gravity is caused by mass, so there can't be gravity before there's mass, right?
Right. So
they're,
yeah. This is a hard question. Yeah. And I don't know if I'm certainly not the best person to answer this, but I don't think we have any super hardcore early universe people like in the first less than a second, the age of the universe after the Big Bang, it was such a foreign environment that things were very dense and very hot. And many of the forces kind of melded together and didn't separate out from that hot mass of everything for, you look at these timelines and it's like in 10 to the negative 31 seconds after the Big Bang, then you have the separation of gravity from the electromagnetic and the strong and weak nuclear forces. And then a little bit longer, and by a little bit longer, I mean 0.00000001 seconds later, then you have separation of this. So I don't remember the exact ordering and I don't remember the timeline, but there are theories for what the breakdown is and how these forces kind of separated out very early on. And I don't remember which is the first one. Do you guys remember? Yeah.
Well, it's not a matter of remembering because we don't know.
Well, no, remember, not us remembering like we were there, but remembering from like
what has been speculated.
What the speculations are. Isn't there a famous book called The First 3 Minutes? I remember reading this like 20 years ago. There's a book. Oh gosh, why do I have to do this online and just show how ignorant I am of this? There's a book called The First 3 Minutes that I remember reading, like 20 years ago. That's all about one of these ideas for the timeline of what happened the first 3 minutes of the universe. It may be somewhat dated because cosmological theories have changed over the last 20 years, but I think it was written, and I remember it being really interesting, but again, somewhat speculative about what was happening in the very, very early universe in terms of the physics and the forces that are present. Yeah. Do you have a question, Roger? No? Okay. Just some interpretive dance. Okay. Oh, wait, you had a third part to your question too. What's the connection between gravity and time?
So gravity is a very strange force. It's very different from the other ones because it's very hard to explain it. But the way gravity works is that matter, as massive objects like the Earth or the Sun or the black holes move, they modify space and time, and so they follow the path that gravity dictates, but they also dictate gravity, right? So they modify space and time. So matter modifies space and time, but it also moves following those paths that matters creates in space and time. So it's not really a force. Like when we think about, the Earth attracting the moon and the sun attracting the Earth, but it's not exactly like that. The way what Einstein, discovered is that gravity does not function as all the other forces. It's more of this interaction between matter and space-time. So that matter modifies both space and time. And in that way, we have this attraction, but it's not really an attraction. So I think that's the connection between time and gravity. Yeah, you need matter to have gravity. Yes. Otherwise, you just have space-time that it's not curved by matter. So it's just
flat space.
Flat space-time.
No, that's, yeah.
Yeah, no, without matter, you don't.
Gravity exists, but it's not, it's
Curves.
Yeah, it warps it. It's very slight, yeah. Right.
Yeah, but then it's not empty. There's galaxies.
Yeah. Yeah. So you can be the space between two massive objects like galaxies, and the space between them is warped simply because of, even though it may be distant from it, it's still feeling the influences of it. So if you're in a place where there's some gravitational attraction that's pulling you somewhere, that means that space-time isn't flat. It's warped because of the gravitational effect that you're feeling. Now, gravitation falls off theoretically, it's the inverse square law. So the farther you get away from me, the square of that is proportional to the gravity. So if I walk, 1 yard away from you, our gravitational attraction is something. And if I walk another yard further, it's the square of that distance instead of just linearly as I walk away. But theoretically that goes to infinity. So it drops off, obviously, so it gets fainter and fainter, but there should be, gravitational attraction. Over a long enough time period, yeah.
Except the universe is expanding.
Unless the universe is expanded, which it is. So it throws in some foibles. Okay. Yeah, here, let me pass the mic to you again. No, great.
Just last question. So with time, would Earth gravity ever change? Like does the mass of the Earth change, and would we ever have our gravity change?
Not unless we get hit by something. Our mass shouldn't change appreciably unless a chunk of the mass of the Earth flies away or something runs into us and adds to our mass.
The Earth is losing a little bit of the atmosphere, little by little.
Yeah.
Very, very little mass. But otherwise, yeah, until it gets eaten up by the sun.
Yeah. Yeah, it should be pretty constant unless we have some massive impactor, like what happened, when the moon formed, we were hit by, the most popular theory is that we were struck by a Mars mass object. It ran into kind of the proto-Earth and expelled a bunch of stuff, which eventually coalesced into the moon. But there are bigger problems than our mass changing by our gravitational pull changing by a little bit. If we get struck by another planet, like it would turn everything into, like, it'd be rock vapor everywhere. It'd be really bad news for us. So yeah, I don't think it'll change by any appreciable amount. Oh man, I promised one guy online that I'd answer his question as the final question. So our last question from Hongdu, I believe was his name, is talking about planets. It seems strange that outer planets like Jupiter and the gas giants have lighter elements that are present, while inner planets have heavier elements. But then this trend doesn't continue because when you get to the sun, it's mostly light elements again. Can anyone explain why this is? Oops. I can talk about it, but I talk about everything, so I want to share the wealth. You guys? Yuhan? Kyle? It's okay. Go for it.
Well, you probably know better than me. I mean, I'm not a planet person, but to my understanding is that light elements are blown away from the inner part of the solar system when the stars are very young. Like when stars are very young, they're very strong winds, and so they can blow away everything that it's like, hydrogen, all the the gas giants elements, carbon dioxide, all of that stuff gets blown away. And so that's why you have to be beyond some distance to be a planet, a giant planet. But we have seen giant planet close by to stars like hot Jupiters, and those are thought to migrate back in, which they haven't done in our solar system. But I think that's the reason, right?
Yeah. Yes. As Ilaria says, those lighter elements, what we refer, or not just the elements, but also the molecules that form from them, we refer to them as volatiles. So water and carbon dioxide, they just get burned off from the interior where it's hot, and they kind of settle in the outer solar system. And so we think that potentially, and in fact, we just had a colloquium about this a couple of days ago, that inside of those gas giants like Jupiter and Saturn, there may be a denser core that's something like Earth or Mars or something like that. It may be different, but we think there's a core, and potentially it accreted, it gathered up all that gas around it and eventually settled onto it because of its gravitational attraction. But that just wouldn't happen in the interior because that gas gets blown out.
Even the water on Earth has arrived later. It has, because the water would have been blown away again. And so it arrived later with this chondrite.
And comets too.
And comets that are like full of water. And I think it's mostly chondrites because of the ratio of isotopes in the hydrogen or something. Yeah, but these types of objects that come from far away, similar to comets.
Right. Isn't that a ton of water? It's a lot of water. Well, there's a lot of comets out there. And there's a lot of time.
There were more comets at the beginning.
Yeah.
But also recently it's not that much.
Yeah. Yeah.
Since you've been around, it's not that much.
Yeah, the time scale over which humans have been recording history and that sort of thing is, thousands of years. And that's very little compared to the billions of years that the Earth has been and the solar system has been around. But yeah, Ilaria is right. There was a period of, it's called the late heavy bombardment. I think it took place about 4 billion years ago. And it was early in the solar system's evolution. There was just a lot of objects around and slamming into each other. And so that potentially is when we got struck by a lot more things. And you can see the residual craters on other structures that don't erode, like Mercury or the moon, and you see all kinds of impacts from this late heavy bombardment that took place in the early part of the solar system. So some of that could have been rocks and asteroids and meteoroids, and some of it could have been things from the outer solar system, which would have had higher composition of volatiles and some of these lighter molecules and atoms and water. Okay, it is 9:03. Thank you, online audience. Sorry about the sound issues earlier. And thank you, in-person audience. Hopefully you got something out of this tonight. Again, our next event will be Astronomy on Tap on January 30th at the Doghouse Beer Garden. 2 science talks, 20-minute long science talks by scientists at JPL and here, and then live music from Jason Achilles and Forrest Mitchell, and astronomy themed pub trivia. And everything's free. Well, yeah, you have to order your own food and beverages, but the science is free. And yeah, we're also in a couple of weeks, we're going to be helping out at the Death Valley National Park Dark Sky Festival, which is taking place February 10th through the 12th. It's a Friday through Sunday. We're giving some talks. There's going to be an astronomy on tap that we're doing at the Badwater Saloon in Stovepipe Wells, which will be super cool. But there'll also be talks from a number of NASA scientists, and there will be a star party, and the skies are obviously much better than you can get here in Pasadena and Los Angeles. So if you're interested, that's free. It's a 4-hour drive from here, but it's also pretty cool. So yeah. For that festival, we're bringing like 10 people, and we're going to carpool to get there. But people can, I mean, we can't provide your transportation for you. Oh no, we're going to go up. We're going to go up on Friday, but I mean, people will show up on like visitors will show up on Saturday or Sunday or whatever. So there's lots of stuff going on, but yeah. Cool. Well, thanks everyone, and have a great weekend.